So now I'm in BST DD Starter, and there's a problem sitting here asking me to design a data definition for binary search trees. And there's a picture here to sort of remind us what the information we're trying to represent is. So let's look at that. This tree, this binary search tree, has a number of what I'm going to call nodes. So here's one here at the root of the tree, and here's another one here, 3ILK. And if we look at those, each of those seems to have 4 parts. It has the number 10 in the top case, which I'm going to call the key. It has the value y in the top case, which I'm going to call the value. And then it has a left subtree and a right subtree. So each of these nodes has 4 parts. And those 4 parts kind of go together. There's the node, the value, the left subtree, the right subtree. That's kind of what makes one of these nodes, is that it has all 4 of those things. So I'm looking at this as compound data. But also notice that these binary search trees, they're arbitrary size. And in particular, they're arbitrary size both in their left branch. The left branch of this tree can be arbitrary sized. And they're arbitrary sized in their right branch. At each node, they can become arbitrary sized going left or going right. That's a little bit different than a list. A list was arbitrary sized in that it could be longer and longer and longer, but that was kind of one direction of it being longer. Here, the tree can be arbitrary sized in its left branch and its right branch. So what that's telling me, and what you'll see, is I'm headed for a compound data definition with 2 self-reference cycles. Here we go. I'll first start with the basics of a compound data definition, a defined struct, and I'm just going to call it node. And I'll call the 4 parts key, val, L, and R. And now I'm going to say a BST, binary search tree, is one of, now I've got to have a well-formed self-referential data definition, so there has to be a base case and self-reference case. So what am I going to use for the base case? Well, where is the base case in this picture? Well, one place it is right here. The node 4DCJ doesn't have a left branch. But because our structure definition has an L for each node, we've got to have something there. What are we going to put there to kind of represent that there's nothing there? That's kind of like the role that empty plays in lists. The rest of every cons has to be something, and empty is what it is to say, well, actually, there's nothing here. In this case, I'm just going to use false. And then for the self-reference case, I'm going to say make node, and let's see, the key is always going to be an integer. The value is always going to be a string. What's the left branch? What's the left branch of the tree going to be? Well, the left branch of 10 is another BST. And the right branch of 10 is another BST. And in fact, if we look at that, that's always true. The left branch of 3ILK is a BST, and so is the right. And what about the left branch of 1ABC? Well, it's an empty BST, or it's false. So it looks like this type comment is going to match that information. Let's do an interpretation. False means no BST, comma, or empty BST. Otherwise, let's see, key is the node key. Val is the node val. L and R are left and right subtrees. Now there's one thing that's missing there, and it's super important. Remember we talked about this invariant, that at each level, all accounts in the left subtree have an account number less than the root, and all accounts in the right subtree have an account number greater than the root. I should note here, I'm calling these nodes instead of accounts, just to kind of make the tree version use slightly different words, just so we don't get confused between the two. We're going to store accounts in this BST, don't worry about that. So what I'm going to do is I'm going to write a thing here called an invariant. And this happens sometimes in more complicated data definitions, where there's something we need to say about the whole tree. It won't be enough to kind of say that it's true of any one particular node. And the invariant is going to be for a given node, key is greater than all keys in its left child, and key is less than all keys in its right child. And there's one more thing that needs to be said, which we didn't have to say before because it was sort of implicit before, but we've also got to say, because of this fact that if the key is less, if the left child is always less and the right child is always greater, that always means the same key never appears twice in the tree. So there's our type comment, our interpretation, and then this additional invariant. Let's do some examples. Let's see, define BST 0, we'll just call that false. And now what I'm going to do is I'm going to build a BST that kind of looks like that picture, or at least I'm going to start building one that looks like that picture. So I'm going to say define BST1 is make node 1 ABC, and then false, false. So that's that node 1ABC. And let's see, define BST4 is make node 4 DCJ, and then I'm going to just put the false for the left branch, and I'll build node 7 right here. I won't give node 7 its very own name. Make node 7 RUF. I'm just showing here that you can build up these complex examples through a combination of using named constants or named example data and not using it. So now let's see, I've got 1 and 4, so I can build 3. And 3 is just has as its left child BST1 and in its right child BST4. And now I'm almost regretting having used such a big example because a lot of typing is going to have to happen here. So we'll just use the magic of editing to make it go a little bit quicker. So there's 42, and then of course for the top of the tree, 10 WHY has as its children 3 and 42. So there we go, we run that and it's all well formed. Now we've got to do the template. I'll just call the parameter t, and we'll also set up for template rules used. Now let's see, the first thing is one of, and there's 2 cases. So I'll go put a cond with 2 question answer pairs. And the first case is false, atomic distinct false, and so we'll just put false question mark of t dot dot dot. And let's see, the second case is this compound here, the make node, compound, and I'll just copy that because it's a lot to type. There we go. So I'll take, this is the else case, and we'll take the compound apart, node key of t, and we'll put a note here that says that this is a integer, node val of t, and we'll put a note here that says that this is a string, node L of t, and we'll put a note here that says that this is a BST, and node R of t, and we'll put a note here that says that this is a BST. And what we'll do is we'll move all of this to there. There we go. So let's see, integer is a primitive type, string is a primitive type, but BST sure as heck isn't a primitive type. That's a self-reference. Node L of t has type BST. So we're going to use the self-reference rule right here. We have to put a natural recursion right there. Fun for BST. And that's the self-reference. And we got another self-reference in the right branch. So we put fun for BST there, and we get rid of the BST comment, and we need an extra paren there. Let's see if that's well formed. It appears to be. It's running without any problems, so we'll comment it out. And now let's look at it. We've got a self-reference cycle here in the type comment that corresponds to this natural recursion in the template. That's in the left branch. That's what's letting the left branch kind of get, at any level, be bigger if it wants to. And we've got another self-reference in the type comment here with a corresponding natural recursion in the template here, and that's what's letting the right branch be bigger at any level. So that looks pretty good. That looks like a data definition for binary search trees.